In this lesson, we're going to talk about activity 2.1 vectors. The objective is to spend a little bit of time looking at some trig review or some trig concepts, and then looking at some stuff around vectors, some vector basics. If you've never messed with sine, cosine, or tangent before, it's nothing to be scared of. In fact, it's actually pretty easy stuff, especially as it relates to right triangle trig. But in this situation, sine, cosine, and tangent simply represent ratios of specific sides of the triangle. So here you can see we have three sides of the triangle. Those sides are going to be designated as an opposite side, an adjacent side, and a hypotenuse. So in this case, or in all cases, the hypotenuse is going to be the angled side, and then the adjacent and opposite sides are going to change depending on which angle you're focusing on. So if I'm focusing on this 30-degree angle, the opposite side would be the side that is directly across it. So that would be this side right here. The adjacent side would be the one that is next to it or adjacent to it. So if, again, depending on which angle, if we move over to the 60-degree angle and we go straight across, that would be our opposite side, so that would make this the opposite side, and adjacent would be next to it, which would be this side here. Okay, and so let's do a quick little example to kind of show you what these ratios look like. So I'm going to pull up my calculator here, and we're going to say that we're going to focus on this 30-degree angle here, and we have sine of the angle is equal to opposite over hypotenuse. So if I take the sine of 30, we're going to find out that the sine of 30 is just a ratio that defines the relationship between this side to this side. So I'm going to punch in 30 right here, and then under trigonometry we're going to do the sine of that. You'll see that it comes out to 0.5. That simply means that the opposite side is always going to be 1/2 of the hypotenuse. So it's as simple as that. So if my hypotenuse were 10 feet long, then my opposite side is going to be 5 feet long. And that relationship is going to hold true regardless of how long this hypotenuse gets or how short it gets. As long as we're at 30 degrees, that relationship will stay the same. And it's going to be the same thing here with cosine. If I wanted to find out, so here let's plug in 30, and we'll go and we'll take the cosine of 30. It says that it is 0.866. So that means that this adjacent side will always be 0.866 the length of the hypotenuse, and so on and so forth. But what if we didn't have a degree? What if they didn't give you a value for degrees, but they gave you two sides instead? So maybe I have my opposite side and I have my hypotenuse side, but I really need this angle right here. And so we're going to stick with our example of a hypotenuse of 10 and a opposite side of 5. So we know the answer should come out to 30. But what we can do is we can use these the inverse sine, cosine, and tangent to allow us to solve for an angle. So in this case, we would take the inverse sine of the opposite side over the hypotenuse. Again, we would be given those values, and that would give us the angle. So in this case, I'm going to take my opposite side, which is 5, because I'm trying to solve for this angle here, and I'm going to divide that by 10, which is the hypotenuse. That gives us 0.5, and then we're going to go and do the inverse sine, and you'll see that that gives us 30 degrees for that angle. And again, the same holds true for cosine and tangent. Just make sure that you're using the correct sides, otherwise you won't get the right answer. Another option that we have, again, this one goes back to finding lengths, though, is say they gave us this side here and this side here, but I don't know my hypotenuse, but I want to know the hypotenuse length. So we can use Pythagorean theorem. Pythagorean theorem states that a squared plus b squared is equal to c squared. So in this case, the sides that we're labeling as opposite and adjacent, it doesn't matter which one of these two you want to use. You can call this one a squared and this one b squared, but you're going to take this side length, square it, add it to this side length squared, and then that's going to give you the hypotenuse squared. So when you take the square root of the c squared, you'll get the length of hypotenuse. So that's another nice little tool that we're going to use here coming up. Okay, so moving into vectors, we're going to be using vectors to represent or to illustrate forces that are, say, within a, whether that be a member or a cable or something like that, some kind of material that's going to carry a load. And we're going to use vectors to help us find out some information about that. So down here on the right, you'll see I have a little vector drawn out. And this little vector, the vector is this line. Right here, we can call that one vector A. And that vector has some characteristics about it that we need to discuss. So one of those things is that all vectors always have, vector quantities have a magnitude and a direction. So in this case, you can see that the vector is going off in a certain direction, which happens to be 60 degrees off of the positive x-axis. And it also has a magnitude, so it's 150 pounds is our magnitude. Okay, and if you kind of think back to our right triangle trig here, we can kind of turn this into a triangle, and that 150 pounds would be our hypotenuse, right? The magnitude is the hypotenuse. Okay, before we go and look at this example and do some other things with this, I wanted to talk a little bit about the grid. So you probably are familiar with the 4 quadrants of your x and y coordinates here. But you have positive x, positive y, negative x, negative y, and in each one of these we have a vector sense. So the sense would be up and to the right, meaning that we have a positive y, positive x. Up and to the left would be a positive y but a negative x, and down and left would be a negative x and negative y, and down and right would be negative y but positive x. So it's important to know what quadrant we're looking at, because direction is going to matter when we start adding additional vectors in here. So we want to make sure we're paying attention to what's positive and what's negative. But all vectors can be broken down into x and y components, and what that means is if we take, for example, if we take this vector and we know that it's pulling 150 pounds and 60 degrees, I know that some of that force, that magnitude there, is pulling to the right, and I know that some of that force is pulling straight up, right? So we have some force in y and we have some force in x. Now we need to break that out and figure out what that actually is. Okay, because especially when we start adding other forces in here, we want to be able to figure out an overall direction, and then the only way to do that is to break it all down into its x and y components. So we're going to do that real quick. I have the example right here, and we're going to take and figure out what is the x component and what is the y component of each one of these, or of this particular vector. So we're going to start out by solving for the x component. So okay, so the x component, we already know that we had our, let's see, so we have sine is equal to opposite over hypotenuse, that's sine of the angle. The cosine of the angle is equal to adjacent over the hypotenuse, and tangent of the angle is equal to opposite over adjacent. So if we go here and we want to find the x component, again, given the 60 degrees, I know that straight across this would be the opposite side, and then next to it would be the adjacent side. I have the hypotenuse, in this case would be 150. So in order for me to find the x component, I have to use cosine. So cosine is going to give us x. So if we take our formula here from cosine, it's going to be the cosine of the angle, so the cosine is 60, is equal to the adjacent side over the hypotenuse. So the adjacent side I don't know. In fact, that's just our x component, so I'm going to put x there. And then over the hypotenuse, I know that's the magnitude of 150. Okay, so what that does is, if we break that down, is the cosine is 60 times 150 gives us a value of 75. Okay, and so that would be 75 pounds. So I know that given this vector, that I have 75 pounds of pull going to the right. Okay, and then if we want to switch that over, we can look at what is the y component. Okay, so we'll try and write this. So the y component, we're going to do a very similar thing, except for I know that the y component is going vertical, so if I follow this angle straight across, that means it's the opposite side. So that tells me that y is going to be, we're going to have to use sine to get y. So we're going to say the sine of the angle, so in this case the sine is 60, equals the opposite side, which is my y component, over 150. So I should have the sine of 60 times 150, and that's going to give you 129.9. I'm just going to, yep, so 129.9. Okay, so that tells me that I've got 75 pounds of force pulling to the right, and I have 129.9 pounds going straight up and down. The sense of this vector would be up and to the right. So we have now broken down, we've taken our vector, we've figured out what our magnitude is, we know our angle, so that's our direction, we know our x component, and we know our y component. And we're going to take that concept and just continue with that moving forward here. Alright, so I'm going to have you pause the video. This is an example. We have a telephone pole with a cable, again at 60 degrees. I want you to pause the video and see if you can break this example down into its x and its y components. Go. Alright, hopefully you were able to solve for that. So I have the answer right here. We have our 60 degrees going straight across. We would get our opposite side, so y component would be needing sine. So sine of 60 is equal to the opposite side over 200. The sine of 60 times 200 is equal to 173.21 for the y component. X, we're going to have to use cosine, and in that situation we solved and we got 100 pounds going in the y, or in the x direction. So hopefully you were able to get that. Let's look at another example. In some cases we're going to have more than one vector that we're going to have to deal with, and so before you get into looking at all of this, I want you to focus right here. So in this first part we have our x and our y coordinate, and we have one, we'll call this a cable. Alright, so somebody's pulling the cable at 150 pounds at 35 degrees. But then we have somebody else with the same attachment point pulling another cable at 45 degrees and 200 pounds. So what we're going to do is we're going to figure out what's called the resultant. And the resultant is basically the overall pull if we were to combine these two together. So if you know if one person's pulling here and another person's pulling here, there's probably going to be a pull, like the two of them together are probably going to move the object in, say, this direction, something like that. So what we want to do is be able to figure that out. And to do that, we're going to figure out the x component for this vector, and we're going to add it with the x component from this vector. And we're going to do the same thing in y. So I'll take the y component here, add it to the y component here, and what we're going to end up with is two coordinates, a coordinate for x and a coordinate for y, which we can then replot on a new graph and solve for the magnitude. So let's do that. So we have our, let's start with the first one. To get the x component out of this vector, we're going to use the angle relative to x, which makes cosine solve for x. So we have the cosine of 35 times the magnitude, which is the hypotenuse, equals 122.87. And we'll do the same thing for this guy while we're talking about x. So we've got the cosine again, cosine of 45 degrees times the magnitude of 200 gives us 141.42. So if we add these two together, what we're figuring out is how much pull we have to the right combined. So with one person or two people pulling, the combined pull in x is 264. In y we do the same thing, but we're using sine. So I've got, in this case, this vector is going up and to the right, so y would be positive. So we have the sine of 35 times the magnitude of 150 gives you 86.4. So that means this person is pulling straight up in y 86.4 pounds. But this person's pulling the other direction. It's actually a negative y. So that's why you see this negative designation. And so I take the sine of 45 times 200 to get my y component here, but I make it negative because of the pull direction. And then when we sum those two up, you'll see that it actually ends up being a negative 55.38. So in other words, the overall pull direction in y is actually a little bit down. Okay, and so now we're going to take that information and we're going to redraw this. So I now know that I'm going 264.29 in x. So we're going to start here at 0, 0. We're going to go to the right 264.29. Okay, and we're going to stop there. And then we're going to go for y. We know we have to go down 55.38. So we're going to come down 55.38. We're going to put a little dot right here, and then we're going to draw a new vector. And that vector is going to represent what's called the resultant vector. In other words, it's the combination of these two vectors. Okay, but now that we have that, we've got it redrawn, we're missing some information. Like, I don't know what's the magnitude of this vector. I also don't know what the angle of this vector or the direction of this vector is. So the first thing we're going to do, we know that we have two sides here. We're going to go ahead and use Pythagorean theorem to do a squared plus b squared equals c squared. So I've got 264.29 squared plus 55.38 squared. That gives me c squared. So if I run that out, take the square root of that, I end up with 270.02 as my magnitude for that vector. Okay, and now so I now have 270.02 for that. Now I need to solve for my angle, and again we'll use the inverse tangent to solve for that, because I have if this is the angle I'm trying to solve for, I have the opposite side and I have the adjacent side. I guess at this point I also have the hypotenuse, but I went ahead and I used tangent. So the inverse tangent of my opposite side, so that would be 55.38, over my adjacent side, 264.29, take the inverse tangent of that, you get 11.83 degrees off of the x-axis. Now you'll notice that I didn't use negative here, or here for that matter, and that's simply because the negative just refers to the direction. So it doesn't necessarily come into play, say, in Pythagorean theorem or in the inverse tangent when you're solving for the angles, but it simply refers to, it's so that we know what direction or what quadrant to place these vectors in. So I'm going to have you, so we're going to take a look, hopefully you were able to follow through that. We're going to take a look now at another example. This is the exact same example you saw in the previous example, but what I've done is I've added another vector here. So I want you to pause the video, and in this case see if you can run through the exact same thing we did here where we had two vectors, and this time you're going to try and solve for the resultant vector, magnitude, and angle. So combine these two together, combine your x's, combine your y's, and see if you can solve for the magnitude and angle. Go. Alright, hopefully you were able to solve for that. Here is the answer. So in this case I just summed all the y's up together in one line. So this would be the y component of vector A plus the y component of vector B, and that would give you 237. And then for the x components, we did the same thing. Here's my x component for vector A. Here's my x component for vector B. It gives me 176. We went ahead, redrew it, and used Pythagorean theorem to get 295.95 for the magnitude. And then again, using inverse tangent of the opposite. So here's your angle. Opposite would be 237.48. And the adjacent would be 176.71. Take the inverse tangent of that and you get 53.36 degrees for your angle.